So let's see how I'm here in the Turing Center. You guys might be hearing a background noise. So let me see if I can go through um, the solutions of the last exam. So the first one, you have a car accelerating. Acceleration is constant. There are two markers. The mark 2, the speed is given, and it's marked separated 3 kilometers, and also have 3 kilometers from here. And we want to know where the car is at 70 kilometers, 70 kilometers per hour. So if acceleration is constant, you can use two conditions. In fact, for instance, here at point zero, the initial velocity is zero, right? Because it starts from zero. So we can use this condition and these conditions to determine the acceleration. How can you do that? You use Bernoulli. V final square is equal to V initial square plus 2a del x. So this is 6 kilometers, right? And this is 0, and this is 140. So then you do your calculation. Wait a second. What is it? So you do your calculation, and then you can find your acceleration, whatever kilometers per hour square. You can also do in meters per second square, but you know. And then once you have the acceleration, you can apply again from this position to whatever position it is. The car is 70 kilometers per hour. So then you do the same equation again. 7 kilometers per hour square is equal to initial square plus 2 times acceleration times your new position. So you have this, and then you can get that. Problem number 2, ball is projected upward. So this is a free fall type of motion, right? And so basically you have a building, the ball goes all the way up and then falls. So it's not a projectile motion, it's a free fall. And I think I did this sketch on the board. So this is time equals 0. So we know this is final position when y is equal to 0. It comes out of the top of a building, and the height of this building is given. So this is 9 meters. 9 meters. And the initial velocity is given 36.3 meters per second. And then we want to find time that takes the ball to strike the floor, so the total time. And where was the ball at halftime? So which means once you calculate this time here, halftime is this. Where the ball is at time halftime. That's what we want to do. So let's do the first one. We want to find the time. So how can we do that? If you use your equation position versus time, I think you can do the trick, right? So final position, when it hits the floor, is 0. Initial position is the height of the building. And then you have the initial velocity. And then you have a quadratic equation, and then you can solve for t. So a quadratic equation is one that is given by some dependence in x given by that, and then your x is equal minus b plus minus square root of b squared minus 4ac divided by 2a. So I think here you're going to have one time that is negative. And so you can cancel that out, so you take only one time. So once you calculate the time, so time is calculated, you divide it by 2, and then you have you can then work to find the position at half time, and then you do the same thing again. Y minus 9 is equal 36.3, and then you take the time you calculated before minus 4.9, make that time, and then the square, and pretty much that's it. The third problem is a projectile motion. So as a projectile motion, okay, so we have a cliff. This is the ocean. The projectile is launched. Oh, I hate this thing. I don't. So projectile is launched with an angle of 30. Oh, I'm sorry, the angle is not given. Angle is not given. There you go. The projectile is launched, and goodness of goodness, your projectile velocities are given. So you have your v naught x, 60 meters per second, and you have your v naught y, which is 175 meters per second. So this is given. So you don't need to worry about decomposing your initial velocity in x and y. That's already given. And it's your projectile. Sorry, it's a bad drawing because so the projectile leaves the cliff and then hits a point B, and what you want to know is what's the magnitude of the velocity at time 21 seconds. So basically we want to know the speed at that time, 21 seconds, and we want to know how high is the cliff. So, oops. So we want to know this height over here, right? Let me see if that's the only thing we need. Yeah. So it's kind of the same problem as we did before. In projectile motion, you have two basic components. One is in x and another in y. So the x component, it gives position at any given point from the origin, and that is x is equal v naught x versus time. And then in y, minus y naught gives position in the y at any given time. And so the initial velocity is 175, positive direction. So we have that. Okay, very good. Let's see what conditions I give. We want to find how high the cliff is. So we want to find y naught. So this is your y equals 0. And it is said the projectile reached the water 40 seconds later, right? So then you can say, okay, y equals 0, and my y naught is equal to the height of the building, so 0 minus height is equal 175 times 40 minus 4.9 times 40 squared. And then from here you can get your height, right? So you have your height. To find the velocity, at time 20 seconds, so velocity in x doesn't change. It's always 60 meters per second. It's the same. The velocity in y you can calculate. Velocity in y is velocity, the initial velocity in y minus 9.8 times the 21 seconds. So you want to find that in 21 seconds. So I can tell this Vy is going to be negative, right? Less than 0, which means the projectile was already going down at the moment. So you're going to have something like this. Here's your V naught x. This is your, which is your Vx, and here's your Vy. So once you calculate those two quantities, Vy is calculated here, and Vx is the same 60. You can apply your Pythagoras, square of this plus the square of this, square root of that sum, and then you have your speed. Okay, that's the problem number 3. Problem number 4. This demands a little bit of calculation. You can do any way you prefer. But basically, you have an airplane. So if you do your orientation like east, north, west, and then south, an airplane heads 30 degrees west of north. So this is north, 30 degrees west of north, that's what it is. So you have an angle here, it's 30 degrees. And then there is a cruise velocity given. So in segment 1, you have a vector A that is equal to 800 kilometers per hour times whatever time it took traveling that much. So you have then how the length of that vector basically, and then it turns 760 degrees east of its original direction. So here's the original direction, right? This is the original direction, 30 degrees west of north. So 76 degrees from that means uh, this is pretty much 76 degrees east of its original direction. So that's it. So east of that direction. So the direction is here, east of that. Okay. Then we got that. So and this defined my vector B, right? So this is my vector B, the segment B. This is my vector A. This is my segmented vector B. And it goes what? It goes 70 kilometers per hour on 1.5 hours. So so you have that much kilometers, right, that went through, and then what? And then it turns due north, right? So you go like this, and go the original 800 kilometers per hour, and then I have my vector C that way. My vector C is 800 kilometers per hour for how many hours? 5 hours. So this is a total 20 kilometers. Okay. So I'm kind of putting here the distance it went through, and then refuse. How far from the starting point the airplane is after landing? What was the average speed? So average speed is simple, right? Let's do the first one. So average speed, the definition of average speed is total distance divided by total time. It's not the displacement, like average velocity is total displacement over time, but average speed is total distance. So what you do here is just take total distance, how many kilometers that airplane cover all that time. So you take whatever number that is and divide it by the total time, which is 3 hours plus 1.5 hours plus 5 hours, and then you're done with that part. So to find the other part, so you have this vector, which is 30, and then it's kind of a complicated here, right? Because it's complicated because of my applet here. Oh, So this angle is 79. So this angle is 79, right? Let me bring my x-axis here. So this angle is 79, right? This angle is 30. So this angle right here is 60. Let's see. So if I put it like this, so this angle is 60. So 60 appear right here. This is 60 degrees. So if this is 79, this is 79, and this is 60. So this angle right here, oops, I don't know why it does that. So this angle over here is the angle 79? No, 76. Sorry, the angle is 76. 76, 76. So this angle is 76. So 76 plus 60 is 136. So to 180 is 44. This is quite best, but only on those. So then you have all your angles you need. And then you have another one like that, right? That's vector A, vector B right there, vector B, and vector C. Then we can add them to find the total distance. We can add them. So how do you do that? This is your vector A is equal to negative A. What's the magnitude of A? Is equal to negative 2,500 cosine of 60. No, cosine of 60. I had direction plus 2,400 sine of 60, or cosine of 30, if you will, in the j hat direction. This is j hat right there. Now vector B is, what is this length of that vector? 1050. Vector B is positive projection. 1050 cosine of 44 I hat direction plus 1050 sine of 44 j hat direction. And then when you go to C is 0 I hat direction plus, it doesn't have, so C doesn't have a projection in the x-axis plus that. So your resultant vector, which is A plus B plus C, is equal sum that you can get that done in x and y. So to find how far, so you want to find the displacement back. So this is your Rx, this is your Ri. So this is simply square root of this plus that, square root, and then the problem solved. So this extra credit is a cool thing to do. So you have your, you have to apply derivative. That was the condition. So x is equal x naught cosine of theta t, and y minus y naught is equal v naught sine theta t minus 4.9 t squared. So this is supposed to be known, right? And to find the maximal height, how do you find the maximal height of that thing, that equation of maximal height? How can you do that? So what do? You take the time here. This is V naught, sorry. V naught cosine theta, right? So you take time out of this equation and then you plug it right there, so that you got y is equal y naught plus v naught sine theta divided by v naught cosine theta x. So I'm just replacing t by this expression right here, minus 4.9. Good morning, how are you?
Good, how are you?
Well, thank you. X over V naught cosine theta, and this is a square. And now what you do, you take dy dx equals 0. So you're going to find points of maximum in your parabola right there. And then you can find at what x this happens, right? You apply the derivative. This is it's going to be 1. So you have an x squared. The derivative is going to be 2x. And then you find an x that depends on theta. And once you find that, um, you can find y, right? You just plug back in this equation. Y is equal y naught plus pretty much tangent theta, right? Sine over cosine is tangent times your x max minus 4.9 divided by v naught cosine theta x maximum, and all of this here is a square. Okay. And to find the maximum range, you do the same thing except you work on this condition here. X is equal v naught cosine theta t, and you take the t when you are calculating your range. So that t is given by so if you go in this equation here, there are two conditions for maximal for 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 this horizontal level. One is that t equals 0, and the other one, when you make y is equal y naught, you can find the time. Sorry, I'm rushing now. You plug it in there, you have an equation of x as a function of theta, and then you do the same nonsense. You apply the derivative of x with respect to theta, and then you find when that nonsense is 0, and then you find a condition on theta for that to happen. I think you have to have 2 theta is equal 90 degrees, and then you're going to get your theta is equal 45 degrees. So the maximum range occurs when you are shooting with an angle of 45 degrees. And pretty much that's it.